For decades, we thought we knew what the universe looked like. Brilliant galaxies, glowing nebulae, stars scattered across the darkness. But the James Webb Space Telescope just revealed something shocking. Most of the universe has been invisible this entire time, hidden behind layers of dust, stretched by cosmic expansion, and radiating in wavelengths our eyes and previous telescopes could never see. Entire populations of galaxies, stellar nurseries birthing thousands of stars, and planetary atmospheres brimming with complex chemistry all concealed until infrared vision finally unmasked reality. What Webb found changes everything we thought we understood about how the cosmos actually works. Galaxies too old. 13 billion years is a long time to wait for something to grow, yet the James Webb Space Telescope found galaxies that had no business existing when the universe was barely 300 million years old. These weren't small, scrappy collections of stars fumbling their way into existence. They were massive, structured, and impossibly mature gleaming spiral arms, dense stellar populations, organized chaos where there should have been only primordial fog. The telescope peered through infrared wavelengths into an epoch cosmologists had mapped with confident predictions, only to discover their timeline was wildly, uncomfortably wrong. The early universe was supposed to be simple. After the Big Bang, hydrogen and helium drifted through expanding space, gradually collapsing under gravity into the first stars. Those stars lived fast, died violently, and seeded the cosmos with heavier elements. Only then, after several generations of stellar death and rebirth, could galaxies begin assembling into the grand structures we recognize today. This process required time, billions of years of it. The models were clear, the physics sound, the observations from Hubble consistent with a universe that built itself slowly, methodically, from the ground up. Webb shattered that narrative within months of operation. Astronomers pointed the telescope toward a patch of sky that appeared empty to every previous instrument, and increased the exposure time until faint smudges of light resolved into fully formed galaxies. The redshift measurements, the stretching of light caused by cosmic expansion, placed these objects at distances corresponding to when the universe was less than 5% of its current age. At that point in cosmic history, galaxies should have been messy, irregular blobs of gas barely held together by gravity. Instead, Webb revealed galaxies with masses equivalent to billions of suns, displaying orderly rotation curves and even hints of spiral structure. The implications ripple outward in uncomfortable directions. If galaxies could assemble this quickly, then something about our understanding of structure formation is fundamentally incomplete. Dark matter, the invisible scaffolding thought to guide galactic assembly, might clump faster than predicted. Early star formation could have been far more efficient than models suggest, converting primordial gas into stars at rates that seem physically improbable. Some astronomers have proposed that supermassive black holes, objects millions of times the mass of the Sun, form directly from collapsing gas clouds, rather than growing gradually through stellar death and accretion. These black holes would act as gravitational seeds, pulling matter together at accelerated rates and jump-starting galaxy formation before the universe had properly cooled. The galaxies Webb found aren't just old, they're too organized, too chemically enriched, too much like their modern descendants to fit comfortably into existing frameworks. Spectroscopic analysis reveals elements like carbon, oxygen, and iron in their light, elements that shouldn't exist in meaningful quantities without multiple generations of supernovae polluting the early cosmos. Yet there they sit, impossibly mature, staring back through 13 billion years of cosmic expansion, as if mocking every careful simulation that placed them centuries later in the timeline. What Webb exposed wasn't just a hidden layer of ancient galaxies. It revealed a hidden truth about cosmic evolution, that the universe assembled itself with breathtaking speed, through mechanisms still only partially understood, in conditions hostile to the orderly progression cosmologists had confidently predicted for decades. Forbidden light. The human eye is a narrow window, sensitive to only a sliver of the electromagnetic spectrum stretching from deep radio waves to high-energy gamma rays. James Webb operates in infrared wavelengths, colors invisible to human perception, existing just beyond the red edge of visibility, where heat radiates and ancient starlight arrives after billions of years of cosmic stretching. This isn't a limitation of the telescope, it's its entire purpose. The universe's most important secrets hide in wavelengths. Our biology was never designed to perceive. Infrared light behaves differently than visible light. It penetrates dust clouds that block optical wavelengths completely, revealing stellar nurseries hidden inside opaque nebulae. It detects heat rather than reflected light, allowing astronomers to observe planets, brown dwarfs, and cooling stellar remnants that emit too little visible radiation to appear in traditional telescopes. Most critically, it captures light from the early universe that has been redshifted, stretched by cosmic expansion during its journey across billions of light years, until wavelengths that left distant galaxies as ultraviolet or visible light arrive at Earth as infrared radiation. Webb's instruments divide infrared light into near-infrared and mid-infrared ranges, each revealing different aspects of cosmic structure. Near-infrared wavelengths capture the light from the oldest, most distant galaxies, pushing back the observable frontier to within 300 million years of the Big Bang. Mid-infrared wavelengths penetrate deeper into dust clouds, exposing the complex organic molecules and icy grains that serve as raw materials for planet formation. The telescope essentially sees in colours that don't exist for human perception wavelengths. Our eyes would register as pure darkness, yet carrying as much information as the visible spectrum we evolved to navigate. The engineering required to observe these forbidden wavelengths borders on the absurd. Infrared detectors must operate at temperatures near absolute zero colder than the cosmic microwave background itself to prevent their own heat from overwhelming the faint signals they're designed to detect. Webb maintains its instruments at roughly 7 Kelvin, achieved through a tennis court-sized sunshield that blocks radiation from the Sun, Earth, and Moon simultaneously. At this temperature, materials behave strangely. Metals become brittle, lubricants freeze solid. Electronics require custom designs to function reliably in conditions that would destroy conventional components within hours. The data Webb collects arrives as raw numbers, photon counts across specific wavelength ranges, requiring sophisticated processing to transform into images human minds can interpret. Scientists assign visible colors to invisible wavelengths, mapping near-infrared to red, mid-infrared to orange and yellow, creating false color images that represent information our eyes could never directly perceive. These images aren't photographs in any traditional sense. They're translations, converting forbidden light into a visual language humans can process, revealing a universe that exists beyond the boundaries of biological perception. It revealed an entire electromagnetic reality, wavelengths carrying information about molecular chemistry, thermal emission, red-shifted ancient light that remained inaccessible until technology extended human perception beyond the narrow band evolution provided. The universe's hidden layer wasn't concealed by location. It was concealed by wavelength, invisible walls. Dust sounds trivial microscopic grains of carbon, silicon, and iron scattered through interstellar space like cosmic soot. Yet these particles, each smaller than the wavelength of visible light, form barriers as impenetrable as stone walls when accumulated across light years of distance. They absorb and scatter optical wavelengths so efficiently that entire regions of active star formation remain completely invisible to traditional telescopes, appearing as dark voids in visible light images despite containing thousands of protostars in various stages of ignition. The James Webb Space Telescope sees through these invisible walls as if they weren't there, revealing stellar nurseries hidden inside the galaxy's most opaque regions. The Eagle Nebula's pillars of creation, perhaps the most iconic astronomical photograph ever captured, appear in Hubble images as towering columns of gas and dust backlit by stellar radiation. Beautiful, certainly, but fundamentally incomplete. The visible light view shows only the illuminated surfaces of these structures, the outer shells where starlight interacts with gas. The interiors remain hidden, concealed by layers of dust too thick for optical wavelengths to penetrate. Webb's infrared instruments pierce straight through, exposing dozens of forming stars buried deep within the pillars, objects that remained completely invisible in every previous observation despite being among the most photographed structures in space. Dust grains form when heavy elements condense in the cooling atmospheres of dying stars, particularly red giants shedding their outer layers and supernovae ejecting processed material into space. These particles, silicates, graphite, organic compounds, drift through the interstellar medium until gravity begins, pulling them into dense molecular clouds. Over millions of years, these clouds collapse under their own weight, fragmenting into smaller clumps that eventually ignite nuclear fusion and become stars. The process happens entirely hidden from visible light, obscured by the very material that makes star formation possible. The physics of this concealment is straightforward. Dust grains are roughly the same size as visible light wavelengths, causing maximum interference through a process called Mie scattering. Blue and green photons scatter more efficiently than red ones, the same mechanism that makes Earth's sky blue, while infrared wavelengths, being longer than the grain size, pass through with minimal deflection. A dust cloud that appears utterly opaque at optical wavelengths becomes nearly transparent in infrared, revealing the warm protostars embedded within, each radiating primarily in wavelengths our eyes cannot perceive. Webb's observations of the Carina Nebula expose this hidden layer with startling clarity. Where Hubble showed dramatic cliffs of gas illuminated by nearby stars, Webb revealed what lies beyond hundreds of previously unknown protostars glowing in infrared, surrounded by swirling disks of gas and dust that will eventually coalesce into planetary systems. Some of these forming stars are so deeply embedded that their visible light emission has been attenuated by factors of millions, reducing brilliant stellar furnaces to invisible whispers in optical wavelengths, while remaining bright and obvious in infrared. The invisible walls aren't barriers preventing star formation. They're the cocoons that make it possible concentrations of material dense enough to collapse gravitationally, shielding forming stars from disruptive radiation while providing the raw material for planetary systems. What Webb exposed wasn't just hidden stars. It revealed the architecture of stellar birth itself, hidden behind curtains of dust that previous generations of telescopes could never penetrate, showing that the galaxy's most active star-forming regions were invisible all along. Time barrier. 400,000 years after the Big Bang, the universe hit a wall, not a physical boundary but a temporal one, a barrier of blazing plasma that rendered the cosmos completely opaque to visible light. The James Webb Space Telescope breaks through this cosmic fog by observing wavelengths that originated before the barrier existed, wavelengths that have been stretched by cosmic expansion until they arrive as infrared radiation carrying information from an era no optical telescope could ever glimpse. This isn't simply looking back in time. It's seeing through a phase transition in the universe's fundamental state, from an ionized soup of particles to the neutral hydrogen that allowed light to travel freely for the first time. The early universe existed in a state called the photon epoch, where temperatures remained high enough to keep electrons stripped from atomic nuclei. Photons couldn't travel more than a few centimeters before colliding with free electrons, scattering endlessly through the dense plasma like torchlight in thick fog. The universe glowed with thermal radiation, but nothing could be seen through it. No structures, no variations, no individual objects. Light and matter were locked in constant interaction, a cosmic traffic jam where photons bounced between particles without making progress. Recombination changed everything. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. This process didn't happen instantly. It occurred over roughly 100,000 years, from redshift z equals 1500 down to z equals 1000, corresponding to temperatures dropping from 3000 to 300 Kelvin. Once electrons were bound to nuclei, photons could finally travel unimpeded. The universe became transparent. The cosmic microwave background, the oldest light we can observe, dates from this moment, carrying information about the density fluctuations that would eventually collapse into galaxies, but revealing nothing about what came before or what formed after. The period following recombination is called the Dark Ages, a label both poetic and accurate. Stars hadn't yet formed. The universe contained only neutral hydrogen gas, dark matter, and the fading glow of the Big Bang stretched into infrared by expansion. This era lasted several 100 million years, a cosmic intermission between the opaque plasma epoch and the first stellar ignition. Traditional telescopes see nothing from this period. There were no stars to observe, no galaxies to image, only darkness gradually assembling itself into structure through gravitational collapse. Webb's infrared instruments pierced through this temporal barrier by detecting light emitted after the Dark Ages ended, when the first stars finally ignited. These population 3 stars, massive, short-lived, composed of primordial hydrogen and helium, radiated primarily in ultraviolet wavelengths. By the time their light reaches Earth, cosmic expansion has stretched these wavelengths by factors of 10 or more, shifting ultraviolet emissions into the infrared spectrum. Webb was designed to observe. The telescope effectively circumvents the opacity barrier by looking in wavelengths that didn't exist during the photon epoch, capturing light from objects so distant and ancient that their radiation has been transformed by the expansion of space itself. The barrier remains absolute for visible light no optical instrument will ever see through the recombination epoch. Yet infrared wavelengths slip past this fundamental limit, carrying messages from the universe's adolescence written in frequencies that cosmic expansion itself created, revealing structures that assembled in darkness before the first galaxies lit their fires. Ancient chemistry. 3 minutes after the Big Bang, the universe consisted almost entirely of hydrogen, helium, and trace amounts of lithium, the only elements primordial nucleosynthesis could forge before temperatures dropped too low for nuclear fusion. The James Webb Space Telescope detects the first molecules that formed from these elements billions of years later, complex chemicals assembled in the cooling atmospheres of early stars and scattered through space by supernova explosions, marking the transition from a chemically sterile cosmos to one capable of supporting the elaborate chemistry that eventually produced planets, oceans, and life itself. Molecular hydrogen formed first, roughly 300 million years after the Big Bang, when temperatures dropped enough for neutral hydrogen atoms to stick together through weak electromagnetic bonds. This molecule, two protons sharing electrons in the simplest possible configuration, became the primary component of the first star-forming clouds. Its formation wasn't trivial. Molecular hydrogen requires specific conditions to assemble. Temperatures below a few thousand Kelvin, sufficient density for atoms to collide frequently, and the absence of ultraviolet radiation intense enough to break the fragile bonds holding the molecule together. In the early universe, these conditions existed only in the densest regions where dark matter had already begun pulling gas into gravitational wells. The first generation of stars changed the chemistry permanently. Population 3 stars massive objects composed purely of primordial material, burned at extreme temperatures, fusing hydrogen into helium, carbon, oxygen, and heavier elements through the CNO cycle and triple alpha process. When these stars exploded as supernovae, they dispersed chemically processed material throughout the surrounding gas, seeding clouds with elements that had never existed before. Carbon, essential for organic chemistry. Oxygen, capable of bonding with nearly everything. Iron, silicon, magnesium building blocks for rocky planets and complex molecules. Webb observes this ancient chemistry through spectroscopy, splitting light from distant galaxies into component wavelengths and identifying the dark absorption lines where specific elements remove photons at characteristic frequencies. Each element leaves a unique signature. Carbon absorbs at 158 nanometers, oxygen at 130 nanometers, iron across multiple ultraviolet wavelengths. By examining which lines appear in light from galaxies observed at different distances, and therefore different epochs in cosmic history, astronomers can trace the chemical evolution of the universe across billions of years, watching metallicity gradually increase as successive generations of stars enrich the interstellar medium. The detection of carbon monoxide in galaxies less than 1 billion years after the Big Bang reveals how quickly complex molecules assembled from the debris of early supernovae. Carbon monoxide requires both carbon and oxygen, elements absent from primordial gas, meaning its presence indicates at least one previous generation of massive stars has already lived and died. Water molecules appear in spectra from similar epochs, hydrogen and oxygen combining in the cooling envelopes of red giants and spreading through space when these stars shed their outer layers. Methane, ammonia, even polycyclic aromatic hydrocarbons, complex ring structures formed through intricate carbon chemistry, emerge in Webb's observations of ancient galaxies, suggesting that the chemical foundations for organic complexity appeared remarkably early in cosmic history. The molecular signatures tell a story of accelerated evolution. The universe didn't wait billions of years to develop chemical complexity. Within the first billion years, stellar death had already scattered enough heavy elements through space to begin assembling the molecular library that would eventually include amino acids, sugars, and the organic precursors necessary for biological chemistry to emerge. Hidden monsters. Supermassive black holes weren't supposed to exist in baby galaxies, yet the James Webb Space Telescope finds them everywhere it looks in the early universe. Gravitational monsters containing millions or billions of solar masses, occupying the centers of galaxies barely 500 million years old. The timeline doesn't work. Black holes grow by consuming matter, and even feeding at the maximum physically possible rate, stellar mass black holes formed from the first supernovae couldn't accumulate enough mass to reach supermassive scale within the available time. These hidden monsters challenge every model of black hole formation, suggesting mechanisms astronomers hadn't seriously considered necessary. The standard formation pathway starts with massive stars. When population 3 stars exhausted their nuclear fuel and collapsed, they left behind black holes perhaps 20 to 100 times the mass of the Sunday. These stellar remnants would then grow through accretion, pulling in surrounding gas and occasionally merging with other black holes, gradually accumulating mass over hundreds of millions of years. The process has a speed limit called the Eddington luminosity, determined by radiation pressure. When matter falls into a black hole, friction heats the accretion disk until it radiates so intensely that the outgoing pressure balances gravitational pull, limiting how quickly additional material can fall inward. Even feeding continuously at this maximum rate, a 100 solar mass black hole requires roughly 800 million years to reach 1 billion solar masses. Webb observes supermassive black holes in galaxies at redshift z equals 10 and beyond, corresponding to when the universe was only 450 million years old. The most massive of these objects contain several hundred million solar masses, requiring growth rates that exceed the Eddington limit by factors of 5 or more, physically impossible if they grew from stellar mass seeds through standard accretion. Something different happened in the early universe. Some mechanism that bypassed the gradual accumulation of mass through stellar death and produced massive black holes almost immediately. One possibility involves direct collapse. Under specific conditions, low metallicity gas in massive clouds exposed to intense ultraviolet radiation, molecular hydrogen formation can be suppressed, preventing the gas from cooling efficiently. Without molecular hydrogen to radiate away energy, the cloud remains hot and unable to fragment into smaller clumps that would form individual stars. Instead, the entire cloud collapses monolithically, creating a single massive object that either forms a supermassive star of 10,000 solar masses or more, which then collapses directly into a black hole, or collapses straight to a black hole without ever igniting fusion. These direct collapse black holes would begin with masses already in the thousands or tens of thousands of solar masses, bypassing the slow stellar evolution pathway entirely. Webb's spectroscopic observations reveal the presence of these hidden monsters through their influence on surrounding gas. Active galactic nuclei, the luminous regions surrounding supermassive black holes actively feeding on infalling material, emit characteristic emission lines from ionized gas accelerated to tremendous velocities. Broad emission lines, where Doppler shifting smears the wavelength across a wide range, indicate gas orbiting close to the black hole at thousands of kilometers per second. The width of these lines directly correlates with the mass of the central object. Through Newtonian mechanics, wider lines mean faster, orbits mean stronger, gravity mean more massive black holes. The discovery reaches beyond simple detection. These objects appear so frequently in early galaxies that they seem integral to galaxy formation itself, not passengers riding along inside developing structures, but architects helping to shape them. Their gravity pulls matter inward, while their radiation pushes it outward, creating feedback loops that regulate star formation rates and determine how galaxies evolve, suggesting the universe built its largest structures around gravitational singularities that shouldn't have existed yet. Ghost galaxies. Between the luminous galaxies catalogued by decades of optical astronomy, the James Webb Space Telescope discovered ghost galaxies' entire stellar systems, so faint and dust-obscured that every previous instrument looked straight through them without registering their existence. These aren't distant objects rendered invisible by cosmic expansion alone. They're nearby structures, sometimes within a few billion light-years, hidden behind such thick veils of dust that their stellar populations emit virtually no visible light, appearing as voids in optical surveys while blazing brightly in Webb's infrared detectors. The universe contained far more galaxies than astronomers had counted, populations that remained completely unknown until infrared instruments finally revealed them. The physics of their invisibility mirrors the dust clouds hiding stellar nurseries, but scaled to galactic proportions. These ghost galaxies undergo extreme episodes of star formation, producing thousands of solar masses worth of new stars annually, rates far exceeding the Milky Way's leisurely pace of 2 or 3 solar masses per year. Rapid star formation generates enormous quantities of dust, as massive stars evolve quickly through their life cycles, shedding material that condenses into microscopic grains. This dust accumulates until it shrouds the entire galaxy, absorbing ultraviolet and visible light from young stars and re-radiating the energy as infrared thermal emission. Optical telescopes searching these regions of sky found nothing: no stellar light, no distinctive colours, no structural features indicating a galaxy's presence. The dust absorption was so complete that these objects essentially vanished from the visible spectrum, creating apparent gaps in cosmic structure where careful galaxy surveys had counted stellar populations. Astronomers knew the universe's total mass exceeded what visible galaxies could account for, but attributing this discrepancy to dark matter left the question of whether normal matter stars and gas might also be hiding in plain sight. Webb's infrared instruments see through the obscuration as if the dust weren't there. The longer wavelengths penetrate the cosmic soot, revealing the thermal glow of dust heated by embedded star formation, and, at near-infrared wavelengths, the direct light from stars themselves. Entire galaxies materialized in Webb's images, where optical surveys had shown only darkness, massive spiral structures, irregular starbursts, even merging systems caught mid-collision, all previously invisible despite occurring at cosmological distances well within the range of ground-based telescopes. The discovery rate proved startling. Deep field observations revealed that roughly 20 to 30% of galaxies in certain epochs, particularly during the peak of cosmic star formation, 8 to 10 billion years ago, had been missed by optical surveys. These ghost galaxies contributed significantly to the universe's total stellar mass budget, meaning previous calculations of how efficiently the cosmos converts gas into stars were systematically underestimating the process. The universe had been more productive than astronomers realized, assembling stellar populations inside dust-shrouded factories that remained invisible until infrared eyes finally pierced the veil. Some ghost galaxies show signs of recent mergers, violent collisions between gas-rich systems that triggered explosive star formation while simultaneously producing the dust clouds that hid the process from view. Others appear as isolated systems undergoing more gradual starbursts, their opacity arising from accumulated dust produced over millions of years of continuous stellar birth. In both cases, the infrared emission patterns reveal galaxies and phases of evolution that optical astronomy simply couldn't observe, capturing moments in galactic development that were invisible to every telescope built before Webb opened its mirror to the sky. The revelation carries implications beyond simple census corrections. Understanding how galaxies evolve requires observing them through all phases of their development, including the dust-obscured episodes where most of their stellar mass assembles. For decades, astronomers studied galaxy evolution with one eye effectively closed, missing entire populations that happened to be hiding behind curtains of their own making. Dark scaffolding. Gravity reveals itself through motion planets orbiting stars, stars orbiting galactic centers, galaxies themselves arranged in vast structures spanning hundreds of millions of light-years. The James Webb Space Telescope maps this dark scaffolding by observing how light bends around invisible mass, tracing the architecture of dark matter through gravitational lensing effects that warp and magnify background galaxies into arcs, rings, and multiple images. This cosmic web of dark matter outweighs visible matter by factors of 5 to 1, forming the gravitational framework around which every luminous structure in the universe assembled, yet remaining completely invisible except through its influence on space itself. Dark matter doesn't emit, absorb, or reflect electromagnetic radiation at any wavelength. It interacts with normal matter only through gravity, making it undetectable through traditional astronomical observation. Its existence emerged from discrepancies between visible mass and gravitational effects. Spiral galaxies rotate too quickly for their visible matter to hold them together. Galaxy clusters contain insufficient luminous mass to prevent their constituent galaxies from flying apart, and the universe's large-scale structure requires more gravitational attraction than visible matter can provide. Something invisible comprises the vast majority of matter in the cosmos. The distribution of dark matter follows patterns predicted by cosmological simulations. Shortly after the Big Bang, dark matter began clumping under its own gravity, forming dense filaments and nodes while leaving vast voids nearly empty. Normal matter, hydrogen and helium gas fell into these gravitational wells, accumulating along the dark matter scaffolding. Where dark matter concentrated most densely, gas clouds collapsed and ignited as the first stars. Galaxies formed at the intersections of dark matter filaments. Clusters assembled where multiple filaments met, and superclusters emerged as the largest gravitationally bound structures in the universe. Webb observes this invisible architecture through gravitational lensing, an effect predicted by Einstein's general relativity. Massive objects curve spacetime, bending light rays passing nearby. When a massive galaxy cluster sits between Earth and a more distant galaxy, the cluster's gravity acts as a lens, distorting the background galaxy's image into elongated arcs, or even complete rings called Einstein rings. The degree of distortion depends directly on the lensing mass. Stronger lensing indicates more matter, both visible and dark. By mapping these distortions across multiple background galaxies at different distances, astronomers reconstruct the three-dimensional distribution of matter in the lensing cluster, revealing dark matter concentrations with remarkable precision. The cosmic Webb structure appears in Webb's deep field images as patterns in how background galaxies are lensed. Regions with strong lensing mark dense nodes of dark matter where galaxy clusters sit. Elongated arcs stretching in specific directions trace filaments connecting these nodes. The absence of lensing indicates voids, vast regions nearly devoid of both dark and visible matter. The overall pattern resembles neural networks or fungal mycelium, a web of connected structures with dense nodes linked by thinner filaments and separated by empty regions. This scaffolding determined where galaxies could form and how they evolved. Galaxies sitting at major filament intersections experienced frequent interactions and mergers, growing rapidly into massive elliptical systems. Galaxies along thinner filaments evolved more peacefully, forming the spiral structures seen throughout the local universe. Galaxies in voids remained small and isolated, starved of the gas influx necessary for vigorous star formation. The entire visible structure of the universe, every galaxy, cluster, and supercluster, reflects the underlying dark matter distribution that assembled during the universe's first few 100 million years. Webb's lensing observations also probe dark matter's properties. The sharpness of lensing features constrains how dark matter particles interact with each other. Too much self-interaction would smooth out the smallest structures, while too little allows dark matter to form dense cores at galactic centers. Current observations suggest dark matter is effectively collisionless, particles passing through each other without friction or electromagnetic interaction, assembling into structures shaped purely by gravity. The invisible framework supporting every visible structure behaves like a ghost. Fluid, massive, influential, yet utterly transparent to everything except space-time itself. Stellar cocoons. Stars don't emerge into space fully formed, they gestate inside stellar cocoons, opaque clouds of gas and dust so dense that the protostellar objects forming within remain hidden from optical observation throughout most of their development. The James Webb Space Telescope peers inside these cocoons through infrared wavelengths, revealing protostars in various stages of formation, from barely condensed cores just beginning to collapse to nearly ignited objects on the verge of initiating nuclear fusion. The hidden layer isn't simply obscured star formation, it's the majority of stellar birth, the critical early phases where stars assemble their mass and develop the properties that determine their entire future evolution. Molecular clouds, the birthplaces of stars, achieve densities far exceeding the interstellar average, packing thousands of hydrogen molecules per cubic centimetre into regions spanning tens to hundreds of light years. At these densities, gravitational attraction begins overwhelming the gas pressure resisting collapse. Small fluctuations in density become amplified through gravity's pull, creating clumps that contract while the rest of the cloud flows inward toward them. These collapsing clumps form the cores from which individual stars or star systems develop, each surrounded by an accretion disk of infalling material and embedded within the larger cloud structure. The collapse generates heat through gravitational compression. Infalling gas converts potential energy to kinetic energy through acceleration, then to thermal energy through collisions. At first, this heat radiates away efficiently through molecular line emission, allowing the core to remain cool and continue contracting. As density increases, the core becomes optically thick to its own radiation. Heat can no longer escape freely, and temperature rises according to thermodynamic compression. Eventually, when core temperatures reach several million Kelvin, hydrogen fusion ignites, and the protostar becomes a true star. This entire sequence occurs hidden from visible light. The surrounding envelope of gas and dust absorbs all optical and ultraviolet radiation from the forming star, preventing any direct observation of the protostar itself. Only infrared wavelengths emitted by the heated dust and capable of penetrating the cloud escape to reveal what's happening inside. Webb detects these infrared signatures, observing protostars at every stage of development by analyzing the spectral characteristics of their emission and the structure of their surrounding envelopes. Class 0 protostars appear as the faintest sources, deeply embedded objects where the central protostar contains less mass than its surrounding envelope. These objects radiate primarily in far infrared wavelengths, their energy output dominated by the gravitational heating of infalling material rather than any internal fusion process. Class 1 protostars show slightly more developed structures, with bipolar outflows, jets of material ejected along the rotation axis becoming visible as the protostar begins clearing material from its immediate vicinity. Class 2 objects, approaching the zero-age main sequence, display prominent circumstellar disks visible in near-infrared wavelengths as the envelope dissipates and the central star becomes detectable. Webb's observations of the Carina Nebula revealed dozens of previously unknown protostars at various evolutionary stages, each surrounded by structures invisible to optical telescopes. Some showed clear disk morphologies with gaps indicating possible planet formation already underway before the star had fully ignited fusion. Others displayed complex envelope structures suggesting multiple protostars forming within the same cocoon, future binary or multiple star systems still embedded in their natal material. A few exhibited powerful outflows punching through the surrounding cloud, the first signs of the eventual dispersal that will reveal the newborn star to visible light observation. The cocoons serve purposes beyond simple obscuration. They provide the raw material for stellar mass accumulation and planetary system formation. The dust within them shields forming planets from intense radiation that would otherwise evaporate their atmospheres. The density gradients and temperature variations create the conditions necessary for different types of planetary bodies to condense rocky planets near the warm protostar, gas and ice giants farther out, where volatile compounds remain solid. By the time a star emerges from its cocoon, much of its future has already been determined by processes that occurred entirely hidden from view, shaping stellar systems through mechanisms that only infrared observation can fully reveal. Water vapor. Atmospheres thousands of light-years away carry water vapor in concentrations that dwarf Earth's entire hydrological cycle, hidden oceans suspended as gas around planets we'll never visit. The James Webb Space Telescope detects these distant reservoirs through spectroscopy, identifying the characteristic absorption signatures water molecules leave when starlight passes through planetary atmospheres during transits. Each molecule absorbs specific wavelengths. Water particularly favors infrared bands at 1.4, 1.9, and 2.7 microns, creating dark lines in the transmission spectrum that reveal not just the molecule's presence, but its abundance, temperature, and vertical distribution through atmospheric layers. The detection method relies on geometry. When an exoplanet passes between its star and Earth, a tiny fraction of starlight filters through the planet's atmospheric limb, the thin shell of gas extending above the solid or liquid surface. Molecules in this atmosphere absorb certain wavelengths while allowing others to pass through unimpeded. By comparing the star's spectrum during transit to its spectrum when the planet isn't blocking any light, astronomers isolate the absorption features created exclusively by the planetary atmosphere. Water's spectral signature emerges as a distinct pattern of absorption bands, unmistakable among the thousands of other molecular species that might exist in alien air. WASP 96b, a gas giant roughly half Jupiter's mass orbiting a sun-like star 1100 light-years away, provided one of Webb's first atmospheric detections. The transmission spectrum showed clear, unambiguous water absorption Not tentative hints requiring statistical analysis, but strong signals confirming water vapor throughout the planet's upper atmosphere. The sheer strength of the detection suggested concentrations far exceeding anything in Earth's atmosphere, water molecules comprising a significant fraction of the observable atmospheric composition, despite surface temperatures exceeding 1000 Kelvin. Hot Jupiters like WASP 9-6b aren't habitable. Their proximity to parent stars creates surface conditions incompatible with liquid water or complex chemistry. Yet their water content reveals something fundamental about planetary formation. Water is among the most common molecules in the universe. After molecular hydrogen, oxygen ranks as the third most abundant element, carbon fourth, nitrogen seventh. These elements naturally combine in cooling gas clouds to form simple molecules, water, methane, ammonia, carbon monoxide, that freeze into ices at sufficient distance from forming stars. Planets assembling beyond the snowline, the distance where water ice becomes stable, incorporate vast quantities of these frozen volatiles into their composition. When planets migrate inward pulled by gravitational interactions with a protoplanetary disk or scattered by encounters with other planets, they carry this water with them. Hot Jupiters likely formed in cold outer regions before spiraling toward their current positions close to stellar surfaces. Their atmospheres preserve evidence of this migration history, water vapor remaining abundant despite temperatures high enough to dissociate many other molecules. The presence of water in these unlikely environments confirms theoretical predictions about planetary migration, while demonstrating that water delivery to inner solar systems occurred commonly throughout galactic history. Webb's observations extend beyond gas giants. TRAPPIST-1, a system containing 7 Earth-sized planets orbiting a cool red dwarf star, 40 light-years away, became a priority target for atmospheric characterization. Several of these planets orbit within the habitable zone where liquid water could exist on rocky surfaces. Early spectroscopic observations search for water vapor in their atmospheres, evidence that would suggest oceans, weather systems, and potentially habitable conditions. The first results showed some planets lack substantial atmospheres, their surfaces scoured by stellar radiation. Others display absorption features consistent with water vapor, though confirming its abundance requires additional observations. The water detections aren't simply confirming expectations, they're quantifying the universe's capacity to create environments where liquid water could persist. Nearly every planetary atmosphere Webb examines contains water vapor in some concentration, from trace amounts in hot, dry worlds to dominant atmospheric constituents in cooler planets. The hidden oceans aren't hiding at all, they're suspended in alien skies, waiting for infrared eyes sensitive enough to read their spectral fingerprints across interstellar distances. Carbon signatures. Life on Earth depends entirely on carbon's chemical versatility, its ability to form long chains, complex rings, and stable bonds with hydrogen, oxygen, nitrogen, and countless other elements. The James Webb Space Telescope finds carbon signatures everywhere it looks in the early universe, detecting the element in stellar atmospheres, planetary systems, interstellar clouds, and distant galaxies still assembling their first stellar populations. Carbon's ubiquity isn't accidental. It's a fundamental product of stellar nucleosynthesis, forged inside dying stars through the triple alpha process and scattered through space by supernova explosions, becoming available for incorporation into everything from rocky planets to organic molecules within the first billion years of cosmic history. The triple alpha process creates carbon through an improbable sequence of nuclear reactions. Inside stars that have exhausted their hydrogen fuel, helium nuclei alpha particles begin fusing at temperatures exceeding 100 million Kelvin. 2 helium nuclei briefly combine to form beryllium-8, an unstable isotope that normally decays within 10, -16 seconds. Occasionally, during this fleeting existence, a third helium nucleus collides with the beryllium before it disintegrates, fusing into stable carbon, 1-2. This reaction requires extraordinary timing and precise energy, matching a resonance discovered by Fred Hoyle in 1954, who predicted its existence because carbon abundance in the universe implied it must be possible. Once carbon exists, it gets dispersed. Red giants shed carbon-rich material as they pulsate and lose mass in stellar winds. Supernovae blast processed carbon throughout the interstellar medium at velocities reaching 10,000 kilometers per second. Within a few million years, supernova ejecta mixes with surrounding gas, enriching molecular clouds with carbon available for incorporation into the next generation of stars and planets. Webb observes this enrichment process at various stages: carbon in the cooling atmospheres of evolved stars, carbon in expanding supernova remnants, carbon in the spectra of early galaxies, indicating multiple stellar generations have already cycled through death and enrichment. The element's spectral signatures appear across multiple wavelengths. Carbon atoms in stellar atmospheres create absorption features in ultraviolet spectra, now redshifted into visible and near-infrared ranges for distant galaxies. Carbon monoxide, the second most abundant molecule in the universe after molecular hydrogen, shows strong absorption at mid-infrared wavelengths, revealing gas temperatures and densities in star-forming regions. Polycyclic aromatic hydrocarbons, complex carbon ring structures produced in carbon-rich stellar winds, emit characteristic fluorescence at specific infrared wavelengths when excited by ultraviolet radiation, creating emission features that dominate the mid-infrared spectra of many galaxies. Webb's detection of carbon monoxide in galaxies less than 1 billion years after the Big Bang demonstrates how rapidly stellar death and chemical enrichment proceeded in the early universe. Carbon monoxide requires both carbon and oxygen, neither present in primordial gas, meaning its presence confirms at least one generation of massive stars has already completed its life cycle. The abundance measured in these early galaxies approaches 10% of what exists in the present-day Milky Way, suggesting enrichment occurred with remarkable efficiency during the universe's first few 100 million years of stellar activity. Planetary atmospheres show carbon in various chemical forms. Hot Jupiters display methane absorption when temperatures allow carbon-hydrogen bonding. Cooler planets show carbon dioxide features, carbon bound to oxygen in the stable configuration favoured at moderate temperatures. Some exoplanet atmospheres contain carbon monoxide despite oxygen's general preference for bonding with hydrogen to form water, suggesting disequilibrium chemistry driven by atmospheric dynamics or stellar radiation. The variety of carbon species reveals how planetary temperature, stellar radiation, and atmospheric composition interact to determine which molecules remain stable. The carbon signatures trace a chemical timeline from stellar death to molecular complexity. Massive stars forge carbon from helium, enrich their surroundings when they explode, provide raw material for molecular cloud chemistry, and seed forming planetary systems with the element necessary for organic chemistry to emerge. Life's building blocks weren't created by biology, they were produced by nuclear physics inside dying stars, scattered through space by violent explosions, and delivered to planetary surfaces through the ordinary processes of cosmic evolution that operated long before the first organism ever assembled itself from primordial chemistry. Frozen worlds. Temperature determines what telescopes can see. Hot objects radiate visible light. Warm objects emit near-infrared, and frozen worlds far from stellar heat glow faintly in mid-infrared wavelengths, their surfaces barely warmer than the cosmic background itself. The James Webb Space Telescope detects these cold planets through thermal emission, observing the dim infrared radiation they generate through residual internal heat, tidal flexing, or the faint warmth of distant sunlight reflected and re-radiated by icy surfaces. These frozen worlds represent the majority of planets in the universe, objects beyond their stars' habitable zones, where water ice becomes stable and temperatures drop toward absolute zero, creating environments radically different from Earth, yet potentially harbouring the conditions necessary for exotic forms of chemistry. Neptune-mass planets orbiting beyond 5 astronomical units from their parent stars occupy a regime where methane, ammonia, and water all freeze into ices, forming solid or liquid layers beneath thick hydrogen-helium atmospheres. Traditional optical telescopes struggle to detect these worlds. They reflect minimal starlight and emit virtually no visible radiation. Even near-infrared observations capture only the brightest atmospheric features. Mid-infrared wavelengths finally reveal their true character, detecting thermal emission from atmospheric layers heated by internal energy sources rather than stellar radiation. Webb observes these planets during secondary eclipse, when the planet passes behind its star from Earth's perspective, by measuring how the system's total infrared output decreases when the planet's thermal emission is blocked. The detected emission spectrum reveals atmospheric composition through molecular absorption features superimposed on the thermal continuum. Methane absorbs strongly at specific mid-infrared wavelengths, creating dark bands in the planet's emission spectrum. Water ice clouds high in the atmosphere scatter and absorb infrared radiation, producing distinct spectral signatures different from water vapor. Ammonia, hydrogen sulfide, and phosphine molecules predicted to exist in cold planetary atmospheres each leave characteristic absorption patterns that allow astronomers to map chemical abundances at different atmospheric pressures and temperatures. Some frozen worlds generate more heat than starlight alone can explain. Tidal heating occurs when gravitational interactions with a parent planet or other moons flex the object's interior, converting orbital energy into heat through friction. Europa and Enceladus, icy moons orbiting Jupiter and Saturn, maintain subsurface liquid oceans through this mechanism, despite receiving minimal solar heating. Webb can detect similar thermal anomalies in exoplanet systems by measuring infrared emission that exceeds predictions based on stellar radiation alone, potentially identifying distant ice moons with geological activity and liquid water hidden beneath frozen surfaces. Trans-Neptunian objects in our own solar system, Kuiper belt bodies, scattered disk objects, and the dwarf planets beyond Neptune's orbit barely emit enough infrared radiation to detect even with Webb's sensitivity. Surface temperatures hover around 40 Kelvin, only slightly above the cosmic microwave background temperature of 2.7 Kelvin. Their thermal emission peaks at wavelengths beyond 100 microns, far into the infrared spectrum where even Webb's instruments lose sensitivity. Yet reflected sunlight at shorter wavelengths allows spectroscopic characterization of surface ices, water, methane, nitrogen, and complex organic compounds frozen into solid matrices that have remained largely unchanged since the solar system's formation 4.5 billion years ago. Rogue planets, worlds ejected from their birth systems through gravitational interactions, drift through interstellar space without any star to warm them. These frozen wanderers emit only the residual heat from their formation and the gradual radioactive decay of elements in their interiors. Brown dwarfs, failed stars too small to sustain hydrogen fusion, cool over billions of years until their surfaces barely glow in infrared. Webb's observations probe these isolated objects. Measuring surface temperatures that reveal their ages, younger brown dwarfs remain warmer from recent formation, while ancient ones have cooled until they're barely distinguishable from frozen planets, their infrared glow marking them as some of the coldest objects detectable in the cosmos beyond the reaches of stellar light. Collision zones. Galaxies don't collide gently. They interpenetrate over hundreds of millions of years in collision zones, where hidden violence triggers the most intense star formation episodes the universe can produce. The James Webb Space Telescope observes these merger events through infrared wavelengths that penetrate the dust clouds generated by galactic encounters, revealing stellar nurseries ignited by gravitational compression, shock waves propagating through molecular gas, and supermassive black holes spiraling toward eventual coalescence. The beauty visible in optical images, graceful tidal tails, luminous bridges connecting galaxies, elegant spiral structures distorted into cosmic artwork, conceals destructive forces that reshape entire stellar populations while paradoxically creating conditions favorable for new generations of stars. When galaxies approach each other, dark matter halos interact first, their gravity reaching across millions of light years to begin pulling the systems together. Stars within each galaxy rarely collide directly. The distances between individual stars are so vast compared to stellar diameters that physical impacts remain statistically improbable, even during head-on galactic mergers. Gas clouds, however, cannot pass through each other unaffected. When molecular clouds from different galaxies meet, they slam together at relative velocities, reaching hundreds of kilometers per second, generating shock fronts that compress gas to densities far exceeding those in isolated clouds. This compression triggers gravitational collapse. Gas that might have remained stable for billions of years suddenly finds itself squeezed beyond the threshold where self-gravity overcomes internal pressure. Entire regions of both galaxies begin forming stars simultaneously, converting gas into stellar populations at rates thousands of times faster than typical spiral galaxies manage during quiescent periods. The resulting starburst episodes can consume a galaxy's entire molecular gas reservoir within a few 100 million years, a cosmic blink compared to the billions of years galaxies normally spend gradually converting gas to stars. Webb's infrared observations cut through the dust produced by these violent star formation episodes. Massive stars, the primary products of starburst activity, live only a few million years before exploding as supernovae, each explosion generating dust grains that absorb optical light while re-radiating energy in infrared wavelengths. Collision zones become so dust-obscured that optical telescopes see only the outer regions where tidal forces have pulled stars into extended streams. The cores, where most star formation occurs, remain hidden behind dust concentrations measured in hundreds of magnitudes of optical extinction, enough to block every visible photon attempting to escape. The antennae galaxies, NGC 4038 and NGC 4039, two spiral systems caught mid-merger roughly 65 million light-years away, provided one of Webb's early demonstrations of this hidden violence. Optical images show the famous tidal tails extending like antennae from the collision site, but the galactic cores appear relatively dim, their structure obscured by dust. Webb's mid-infrared view reveals the truth: dozens of compact, ultra-bright sources marking regions where molecular clouds have collapsed into stellar clusters containing tens of thousands of young stars each, their combined luminosity exceeding entire small galaxies, despite being packed into regions only a few hundred light-years across. Supermassive black holes at galactic centers experience their own violent interactions. As galaxies merge, their central black holes sink toward the combined system's gravitational center through dynamical friction gravitational interactions with surrounding stars that gradually drain orbital energy. Eventually, the black holes form a binary system, orbiting each other while accreting gas funneled inward by the merger. These active galactic nuclei emit prodigious radiation, ionizing surrounding gas and launching jets of relativistic particles that can suppress or enhance star formation depending on their interaction with molecular clouds. The collision zones reshape galactic morphology permanently. Spiral structures dissolve as tidal forces redistribute angular momentum. Gas settles into new configurations, sometimes forming rotating disks that eventually rebuild spiral patterns, other times creating pressure-supported elliptical galaxies where stars orbit on random trajectories rather than organized rotation. The violence creates beauty through destruction, forging new structures from gravitational chaos while briefly illuminating the process through starbursts that outshine everything else in the merged system. Chemical codes. Every molecule absorbs and emits light at wavelengths determined by its quantum mechanical energy levels, chemical codes written in the language of photons that the James Webb Space Telescope reads to identify molecular species across cosmic distances. Water absorbs at 1.4, 1.9, and 2.7 microns. Carbon dioxide shows strong bands at 4.3 and 15 microns. Methane creates absorption features at 3.3, 7.7, and 8.6 microns. These wavelengths aren't arbitrary, they correspond to specific vibrational and rotational transitions within molecular structures, each molecule possessing a unique combination of energy levels that functions as an unmistakable, spectroscopic fingerprint no other compound can replicate. The physics behind these fingerprints operates at the atomic scale. Molecules are held together by chemical bonds, shared or transferred electrons, creating electromagnetic forces between nuclei. These bonds behave like springs connecting masses, allowing molecules to vibrate in specific patterns called vibrational modes. A water molecule, for instance, can stretch symmetrically with both hydrogen atoms moving away from oxygen simultaneously, stretch asymmetrically with one hydrogen moving while the other remains stationary, or bend with the hydrogen atoms moving closer together or farther apart, while the oxygen-hydrogen bond lengths stay constant. Each vibrational mode requires a specific amount of energy to excite, and photons carry quantized energy determined by their wavelength through Planck's relationship E equals h times c divided by wavelength. When light passes through molecular gas, photons with exactly the right energy get absorbed, promoting molecules from ground states into excited vibrational states. The molecule then releases this energy, usually by emitting a photon in a random direction, creating a dark absorption line in the transmitted spectrum at the wavelength corresponding to that transition's energy. Rotational transitions add additional structure to molecular spectra. Molecules rotate as well as vibrate, and quantum mechanics restricts rotational motion to discrete energy levels just as it restricts vibrational states. Transitions between rotational levels require less energy than vibrational transitions, creating absorption features at longer infrared wavelengths. The spacing between rotational lines depends on molecular geometry. Linear molecules like carbon dioxide show different patterns than bent molecules like water or symmetric molecules like methane. These patterns make molecular identification remarkably robust even when individual lines appear weak or partially obscured by overlapping features from other species. Webb spectrographs disperse infrared light into component wavelengths with sufficient resolution to distinguish between closely spaced absorption lines. The near-spec instrument achieves spectral resolution exceeding 2000, meaning it can differentiate wavelengths separated by less than 1 part in 2000, enough to resolve individual rotational lines within vibrational bands and identify molecular species even when multiple compounds contribute. Overlapping features. The MIRI instrument extends this capability to longer mid-infrared wavelengths, where larger molecules and complex organic compounds show their strongest transitions. Isotopic variations create subtle shifts in molecular codes. Carbon 1,3, a stable isotope comprising roughly 1% of natural carbon, forms molecules slightly heavier than those built from common carbon 1,2. This mass difference changes vibrational frequencies by small but measurable amounts, creating isotopic lines slightly offset from the main molecular absorption features. By measuring the ratio of carbon 1,3 to carbon 12 inches carbon dioxide or carbon monoxide observed in distant galaxies or exoplanet atmospheres, astronomers can trace chemical processing history. Stellar nucleosynthesis produces different isotopic ratios than primordial material, and biological processes preferentially incorporate lighter isotopes, potentially offering biosignature detection methods. Temperature and pressure broaden spectral lines through collisional and thermal effects. Hot molecules move faster, creating Doppler shifts that smear absorption features across wider wavelength ranges. Dense atmospheres produce frequent molecular collisions that interrupt excited states before they can emit photons, broadening lines through pressure effects. These broadening mechanisms encode information about physical conditions by measuring line shapes and widths. Astronomers determine gas temperatures, pressures, and even wind velocities in objects ranging from protoplanetary disks to exoplanet atmospheres to star-forming regions in distant galaxies, reading environmental conditions from the subtle modifications molecules impose on their own spectroscopic codes. Atmosphere secrets. Starlight filtering through alien atmospheres thousands of light-years away carries secrets about air we'll never breathe, revealing chemical compositions, temperature profiles, and atmospheric dynamics through the James Webb Space Telescope's analysis of transmission spectra. The method exploits planetary transits, those brief alignments when exoplanets pass directly between their host stars and Earth, blocking a fraction of stellar light while allowing a much smaller fraction to pass through the planetary atmosphere's limb. During these transits, atoms and molecules in the atmospheric layers absorb specific wavelengths, imprinting absorption features onto the stellar spectrum that reveal which chemical species exist at what altitudes, temperatures, and abundances in atmospheres separated from us by distances no spacecraft could ever cross. The observable signal is extraordinarily small. A Jupiter-sized planet blocks roughly 1% of its host star's light during transit. The atmosphere, a thin shell extending perhaps 1/10 of a planetary radius above the visible surface, blocks an additional 0.01% when atmospheric constituents absorb at their characteristic wavelengths. Detecting this tiny excess absorption requires comparing the star's spectrum during transit to observations taken before and after, subtracting the stellar contribution to isolate the atmospheric signal. Webb sensitivity makes these measurements possible even for Earth-sized planets around Sun-like stars. Observations impossible for previous generations of telescopes. WASP 39b, a Saturn-mass planet orbiting a Sun-like star, 700 light-years away, became one of Webb's first detailed atmospheric characterization targets. The transmission spectrum revealed water vapor, carbon dioxide, sodium, potassium, and surprisingly clear signs of sulfur dioxide, a molecule produced through photochemistry when ultraviolet light breaks apart other sulfur-bearing compounds high in the atmosphere. The sulfur dioxide detection demonstrated Webb's capability to identify not just abundant atmospheric constituents, but trace species produced by complex chemical reactions, opening possibilities for characterizing atmospheric chemistry on rocky planets where such processes might indicate biological activity. Temperature structure emerges from analyzing how absorption features vary with wavelength and altitude. Molecules absorb most strongly in atmospheric layers where temperatures allow them to remain gaseous and where pressures create optimal line strengths. By measuring absorption depths across multiple wavelengths corresponding to transitions requiring different energies, astronomers reconstruct vertical temperature profiles. Some exoplanet atmospheres show temperature inversions hot upper layers above cooler mid-atmosphere regions, indicating the presence of compounds that absorb stellar radiation efficiently. Others display temperature profiles decreasing steadily with altitude, suggesting minimal high-altitude heating. Cloud layers complicate spectroscopic interpretation by blocking light before it can interact with atmospheric molecules at lower altitudes. High-altitude hazes composed of photochemical products or condensed droplets scatter short-wavelength light more efficiently than long wavelengths, creating spectral slopes that obscure molecular absorption features. Some hot Jupiters show nearly featureless transmission spectra, their atmospheric signals suppressed by thick clouds that prevent light from probing deeper atmospheric layers where most molecular absorption occurs. Webb's extended wavelength coverage helps mitigate this limitation. Clouds affect different wavelengths differently, and by observing across Webb's full infrared range, astronomers can sometimes identify molecules even in cloudy atmospheres through absorption features that peak at wavelengths where cloud opacity drops. Atmospheric escape becomes detectable through extended absorption features far from the planet's visible edge. Hydrogen and helium, being light elements, can achieve escape velocity when heated by intense stellar radiation. These escaping atoms form extended envelopes around hot planets, absorbing starlight at characteristic wavelengths, hydrogen at Lyman alpha in ultraviolet, helium at 10830 angstroms in near-infrared. Webb observes helium escape in real time, measuring how much atmosphere planets lose to space and constraining evolutionary models that predict whether hot planets can retain substantial atmospheres over billions of years or gradually boil away into rocky cores stripped of their primordial envelopes. Rogue wanderers. Darkness between stars isn't empty, it harbours rogue wanderers, planets cast from their birth systems through gravitational violence, drifting alone through interstellar space without suns to warm them or illuminate their existence. The James Webb Space Telescope detects these orphaned worlds through the faint infrared glow they emit from residual formation heat and the slow radioactive decay of elements in their cores, thermal signatures so dim that they appear only in the longest wavelength observations, where even the coldest objects still radiate detectably. Current estimates suggest rogue planets may outnumber stars in the Milky Way, a hidden population of worlds existing in perpetual night, their surfaces frozen at temperatures barely above the cosmic microwave background, yet some potentially harbouring liquid water in subsurface oceans, heated by tidal forces or geological activity. The ejection mechanism that creates rogue planets operates during the chaotic early phases of planetary system formation. When multiple gas giants form in a protoplanetary disk, their gravitational interactions often become unstable. Orbital resonances amplify perturbations, eventually leading to close encounters where planets scatter each other onto new trajectories. The lightest planet in these interactions typically receives the largest velocity change, sometimes enough to exceed the star system's escape velocity. Within a few million years, this planet finds itself on an unbound orbit, receding from its birth star at velocities reaching tens of kilometers per second, destined to spend billions of years traversing interstellar space. Some rogue planets form through direct gravitational collapse rather than ejection. In regions of molecular clouds too dense for stars but containing enough material to produce planetary mass objects, gas can collapse directly into Jupiter mass bodies without ever orbiting a star. These objects, sometimes called sub-brown dwarfs or planetary mass objects, blur the distinction between planets and failed stars. They form like stars through cloud fragmentation but end up with masses below the 13 Jupiter mass threshold necessary to fuse deuterium. Webb observes populations of these objects in young star-forming regions, their infrared emission revealing surface temperatures of several hundred Kelvin, warm by interstellar standards but far cooler than stars. Detecting rogue planets requires extraordinary sensitivity. Unlike exoplanets that periodically transit host stars or induce detectable stellar wobbles, rogue planets provide no such conveniences. They emit no reflected starlight and generate only the faintest thermal radiation from internal heat sources. Webb's observations target star-forming regions where recently ejected planets remain warm enough to glow detectably in mid-infrared wavelengths. Older rogue planets, those ejected billions of years ago and having cooled to temperatures approaching 50 Kelvin, remain essentially invisible even to Webb's instruments, their thermal emission shifted to far infrared wavelengths beyond the telescope's sensitivity range. Gravitational microlensing offers an alternative detection method that reveals rogue planets indirectly. When a massive object passes between Earth and a distant star, its gravity bends space sufficiently to focus the background starlight, temporarily brightening the star in a characteristic pattern lasting hours to days. Planets produce shorter duration events than stars, typically lasting hours, with the exact duration depending on planetary mass and relative velocities. Ground-based microlensing surveys have detected several dozen candidate rogue planets through these brief brightening events, suggesting the population totals billions of objects throughout the galaxy. Surface conditions on rogue planets defy terrestrial intuition. Without stellar heating, atmospheric temperatures drop until gases freeze solid. Nitrogen, oxygen, and carbon dioxide atmospheric constituents on Earth condense as ice is coating the surface. Water ice behaves like bedrock, forming geological structures shaped by cryovolcanism and tectonic processes operating at temperatures where water's mechanical properties resemble silicate rocks on Earth. Yet beneath this frozen surface, internal heat sources might maintain liquid water oceans, particularly in massive rogue planets where thick icy crusts provide insulation while tidal heating from large moons or residual accretion. Heat keeps subsurface layers above freezing temperatures. The existence of rogue planets transforms estimates of where life might emerge. Planetary systems orbiting stars represent only one environment where liquid water could persist. Rogue planets with sufficient internal heating might sustain habitable subsurface oceans for billions of years, isolated ecosystems evolving in complete darkness, deriving energy from chemical gradients rather than photosynthesis, hidden in wandering worlds that drift through space undetected, except for the faint thermal whisper that reveals their passage through the void. Dying stars. Red giants don't simply fade. They die through hidden layers of stellar death, shedding outer envelopes in pulsating waves while their cores collapse toward the degenerate states that will become white dwarfs, neutron stars, or black holes depending on initial mass. The James Webb Space Telescope observes these death throes through infrared wavelengths that penetrate the dust shells ejected during late stellar evolution, revealing the complex structures surrounding dying stars, circumstellar disks, bipolar outflows, nested shells from multiple ejection episodes, and capturing the transition from nuclear-burning star to stellar remnant in unprecedented detail. These observations map the final chapters of stellar evolution. A nuclear-burning star, the processes through which stars return their nuclear process material to the interstellar medium and seed space, with the heavy elements necessary for rocky planets and biological chemistry. The death sequence begins when core hydrogen exhausts. Without fusion pressure to counteract gravity, the core contracts and heats until temperatures reach 100 million Kelvin, hot enough to ignite helium fusion through the triple alpha process. The sudden energy release causes the core to expand, pushing outer layers outward until the star swells to hundreds of times its original radius. Surface temperatures drop as the photosphere expands, shifting the star's emission from visible wavelengths into infrared. The star becomes a red giant, luminous but cool, its bloated envelope barely held by gravity while the core burns helium into carbon and oxygen. Helium burning lasts only a fraction of the hydrogen burning lifetime, perhaps 100 million years for a sun-like star compared to 10 billion years on the main sequence. When helium exhausts, the core again contracts. Stars below 8 solar masses never reach temperatures necessary to fuse carbon, leaving them with inert carbon-oxygen cores surrounded by thin shells where helium and hydrogen fusion continue. These shell-burning phases prove unstable, producing thermal pulses, brief episodes where helium fusion suddenly intensifies, ejecting material from the stellar surface in violent pulsations that gradually strip away the entire envelope. The ejected material forms planetary nebulae, misleadingly named objects that have nothing to do with planets but instead represent the final gaseous remnants of dying stars, illuminated by ultraviolet radiation from the exposed stellar core. Webb observes these nebulae in extraordinary detail. revealing structures invisible at optical wavelengths. The Ring Nebula, M57, appears in visible light as a simple elliptical shell, but Webb's infrared images expose complex filamentary structures, nested shells from multiple ejection events, and dusty clumps where molecules have condensed from the cooling gas. The level of detail suggests turbulent, asymmetric mass loss rather than smooth spherical outflows. More massive stars undergo even more dramatic deaths. When cores exceed 8 solar masses, carbon fusion ignites, followed by neon, oxygen, and silicon burning in successive shells surrounding an iron core. Iron cannot release energy through fusion. It represents the most stable nuclear configuration, the endpoint of stellar nucleosynthesis. When the iron core exceeds 1.4 solar masses, electron degeneracy pressure can no longer support it against gravity. The core collapses catastrophically, from thousands of kilometers in diameter to perhaps 20 kilometers in less than a second, releasing gravitational potential energy equivalent to 100 times the Sun's entire lifetime luminosity output. This energy drives supernova explosions that outshine entire galaxies for weeks. The shockwave tears through overlying stellar layers, ejecting them at velocities exceeding 10,000 kilometers per second. While explosive nucleosynthesis creates elements heavier than iron through rapid neutron capture, Webb observes supernova remnants centuries after their explosions, mapping the distribution of elements synthesized during the final moments: iron, nickel, cobalt from the core regions, oxygen, sulfur, silicon from intermediate layers, and trace amounts of gold, platinum, and uranium created during the explosion itself. The remnant core follows different evolutionary paths depending on mass. Cores between 1.4 and roughly 2.5 solar masses become neutron stars, city-sized objects with densities exceeding atomic nuclei, supported against further collapse by neutron degeneracy pressure. More massive cores overcome even this resistance, collapsing past the Schwarzschild radius to form black holes. Webb cannot observe these remnants directly, but detects their presence through interactions with surrounding material accretion disks, glowing in X-rays, jets of relativistic particles, and gravitational waves from merging remnants detected by LIGO and Virgo observatories. The hidden layers of stellar death prove essential for cosmic chemical evolution. Stars forge elements through fusion, but only return them to space through mass loss and explosions. Without stellar death, the universe would remain composed almost entirely of primordial hydrogen and helium, incapable of producing rocky planets or organic chemistry, sterile across every imaginable wavelength. Primordial seeds. Quantum fluctuations during cosmic inflation planted primordial seeds, infinitesimal density variations in the early universe that gravity amplified over billions of years into every galaxy, cluster, and cosmic structure visible today. The James Webb Space Telescope observes the mature products of these ancient perturbations, galaxies formed from gas that collapsed into the gravitational wells created by tiny quantum fluctuations, when the universe was smaller than a proton, revealing how microscopic uncertainty at the Planck scale cascaded through cosmic evolution to produce the large-scale structure spanning billions of light-years. The hidden origins of everything trace back to quantum mechanics, operating during the universe's first fraction of a second. Random fluctuations frozen into classical density perturbations by inflationary expansion. Inflation theory proposes that the universe underwent exponential expansion during its first 10, -36 to 10, -32 seconds, driven by a scalar field called the inflaton. During this brief period, space expanded by factors exceeding 10^26, stretching quantum fluctuations in the inflaton field across cosmic scales. These fluctuations, originally subject to Heisenberg uncertainty at subatomic scales, became classical density perturbations, regions slightly denser or less dense than average. Their amplitude set by quantum mechanical principles, but their evolution governed by gravity and cosmic expansion. The cosmic microwave background preserves evidence of these primordial fluctuations. Temperature variations across the sky, typically only tens of microkelvin, map the density field when the universe became transparent 380,000 years after the Big Bang. Regions that appear slightly hotter correspond to overdense zones where gravitational potential wells blue-shifted photons through the Sachs-Wolf effect. Cooler regions mark underdense zones. The statistical properties of these temperature fluctuations encode information about inflation itself, the amplitude, spectral index, and possible tensor modes that would indicate primordial gravitational waves. Gravity amplified these tiny initial perturbations through cosmic time. Overdense regions attracted more matter, becoming denser still. Dark matter collapsed first, being unaffected by radiation pressure that prevented normal matter from collapsing until after recombination. By several 100 million years after the Big Bang, dark matter had formed distinct halos ranging from millions to billions of solar masses. Normal matter fell into these halos, eventually cooling and fragmenting to form the first stars. Webb observes galaxies at redshift z equals 11 and beyond, corresponding to when the universe was only 400 million years old, revealing the early stages of this hierarchical assembly process. The power spectrum of density fluctuations determines which structures form first and how they evolve. Inflation predicts a nearly scale-invariant spectrum fluctuations, with similar amplitudes across a wide range of scales. This prediction matches observations remarkably well, with small deviations from perfect scale invariance constraining inflationary models. The primordial power spectrum explains why galaxies form in a bottom-up hierarchy, with smaller objects assembling first and larger structures building through mergers, rather than forming all at once or in a top-down sequence where large structures fragment into smaller ones. Webb's observations of the earliest galaxies' test predictions derive from primordial fluctuations. The abundance of galaxies at high redshift, their masses, clustering properties, and chemical compositions all depend on the initial conditions set during inflation. Discrepancies between predictions and observations, such as the unexpected number of massive galaxies Webb found at redshift z exceeding 10 force refinements to models of early star formation, black hole growth, and dark matter properties, revealing aspects of cosmic evolution that remained hidden until infrared instruments finally captured light from the universe's first billion years. The connection between quantum fluctuations and galactic structure represents one of physics' most profound achievements, linking the smallest and largest scales in nature through a continuous chain of causation spanning 14 billion years. Every galaxy traces its existence to quantum uncertainty, operating when the observable universe fit within a space smaller than an atomic nucleus. Random fluctuations preserved by inflation and amplified by gravity into the cosmic web stretching across billions of light-years of space. Reionization curtain. Neutral hydrogen fog filled the universe for hundreds of millions of years after recombination. A reionization curtain that absorbed ultraviolet light and rendered the cosmos opaque until the first massive stars ignited and began tearing electrons from atoms throughout intergalactic space. The James Webb Space Telescope observes galaxies during this transformation, capturing the epoch when intense stellar radiation gradually converted neutral hydrogen back into ionized plasma, creating expanding bubbles of transparency that eventually merged to make the universe we observe today, one where light travels freely across cosmic distances. This process wasn't instantaneous. It occurred gradually from redshift z equals 15 down to z equals 6, corresponding to between 200 million and 1 billion years after the Big Bang, as successive generations of massive stars pumped ultraviolet photons into their surroundings. The neutral hydrogen epoch began when recombination allowed electrons and protons to combine into stable atoms roughly 380,000 years after the Big Bang. This transition made the universe transparent to the cosmic microwave background, but created a new problem. Neutral hydrogen efficiently absorbs photons with wavelengths shorter than 121.6 nanometers, the energy required to ionize hydrogen atoms. Any ultraviolet light attempting to travel through this neutral medium got absorbed within short distances, leaving the universe effectively opaque at wavelengths where the first stars radiated most intensely. Population 3 stars changed everything. These massive objects, perhaps 100 to 300 times the Sun's mass, burned incredibly hot, with surface temperatures exceeding 50,000 Kelvin. At these temperatures, stars emit copious ultraviolet radiation capable of ionizing hydrogen. Each massive star created an ionized bubble in its surrounding gas, a region where photons had stripped electrons from hydrogen atoms. These bubbles initially remained small, perhaps a few light-years across, limited by the star's luminosity and the density of surrounding neutral gas. As more stars formed, their individual ionized bubbles began encountering each other. Where bubbles met, they merged, creating larger ionized regions surrounding star-forming galaxies. The process accelerated. Each new star added its ionizing photons to regions already partially cleared, and galaxies formed preferentially in overdense regions where ionized bubbles grew fastest. Webb observes galaxies at various stages of this process, some surrounded by substantial ionized regions, others still embedded in neutral gas, showing strong Lyman alpha absorption from intervening hydrogen. The reionization process wasn't uniform. Dense regions ionized first, where vigorous star formation produced sufficient ultraviolet flux to overcome hydrogen's resistance. Underdense voids remained neutral longer, their sparse gas clouds receiving less stellar radiation. By redshift Z equals 7, roughly 750 million years after the Big Bang, the universe had become mostly ionized, though neutral pockets persisted in the lowest density regions. Complete reionization, the point where neutral hydrogen fractions dropped below 1% throughout intergalactic space, occurred around redshift Z equals 6, approximately 1 billion years after the Big Bang. Webb identifies reionized regions through several observational signatures. Lyman alpha emission from galaxies, ultraviolet light produced when electrons recombine with ionized hydrogen, appears bright only if surrounding gas is already ionized. In neutral regions, this emission gets absorbed before reaching telescopes. Galaxies showing strong Lyman alpha emission therefore reside within ionized bubbles, while galaxies with suppressed Lyman alpha remain embedded in neutral hydrogen. By mapping which galaxies show Lyman alpha emission at different redshifts, astronomers reconstruct the growth of ionized regions over cosmic time. The Gunn-Peterson trough provides another diagnostic tool. Neutral hydrogen in the intergalactic medium absorbs photons at the Lyman alpha wavelength and bluer wavelengths, creating complete absorption in galaxy spectra shortward of 121.6 nanometers in the galaxy's rest frame. Webb observes this effect in high redshift quasar spectra, where the Gunn-Peterson trough appears and disappears depending on whether light travels through neutral or ionized regions, mapping the patchwork ionization state during reionization final stages. The reionization curtain represents the universe's last major opacity transition. Before this epoch, the cosmos had been opaque since shortly after the Big Bang. After reionization completed, ultraviolet and visible light could finally propagate across cosmic distances without absorption, enabling the optical universe we observe today, a transparent medium where light from the earliest galaxies reaches us after traversing billions of light-years of intervening space. First starlight. Darkness ended not gradually, but through violent ignition. First starlight blazing from population 3 objects so massive and luminous they lived only a few million years before exploding. Yet their brief existence transformed the universe from a primordial fog into something beginning to resemble the galaxy-filled cosmos we inhabit. The James Webb Space Telescope searches for evidence of these earliest luminous objects, detecting galaxies at redshift Z exceeding 13, where population 3 star signatures might appear, ultraviolet emission patterns indicating metal-free stellar populations, unusual helium abundances, or the distinctive chemical yields from pair instability supernovae that characterized the deaths of the first stellar generation. Finding these signatures proves extraordinarily difficult, because first starlight appeared perhaps only 100 to 200 million years after the Big Bang, and even Webb's sensitivity barely reaches this epoch. Population 3 star formation required specific conditions achievable only in the early universe. Dark matter halos with masses exceeding 1 million solar masses provided sufficient gravitational potential to trap primordial gas composed almost entirely of hydrogen and helium. Within these halos, molecular hydrogen formed through slow chemical reactions, creating the only available coolant capable of radiating away gravitational heating and allowing gas clouds to collapse. The cooling efficiency remained low. Molecular hydrogen radiates less effectively than the metal-enriched molecules dominating modern star formation, meaning primordial gas clouds had to be more massive and hotter than destructive, contemporary molecular clouds before gravitational collapse could proceed. The resulting stars emerged with extraordinary masses. Simulations suggest typical population 3 stars contained 50 to 300 solar masses, far exceeding the masses of stars forming in today's metal-rich environments. These behemoths burned through their hydrogen fuel in only 2 to 3 million years, fusing lighter elements into carbon, oxygen, and heavier nuclei at prodigious rates while radiating 10,000 to 1 million times the sun's luminosity. Their surface temperatures exceeded 50,000 Kelvin, making them intense ultraviolet sources capable of ionizing surrounding hydrogen across distances spanning hundreds of light years. Webb attempts to detect the integrated light from these early stellar populations by observing the most distant galaxies accessible at infrared wavelengths. Galaxies at redshift Z equals 14, corresponding to roughly 300 million years after the Big Bang, represent the frontier of current observations. At these distances, cosmic expansion has stretched ultraviolet light emitted by hot population 3 stars into near-infrared wavelengths where Webb's instruments achieve maximum sensitivity. The spectroscopic signatures prove subtle metal-free atmospheres, produce different absorption patterns than metal-enriched stars, and the lack of molecular coolants affects stellar structure in ways that modify temperature and luminosity relationships. Pair instability supernovae represent the most distinctive signature of population 3 star death. Stars exceeding roughly 140 solar masses develop cores hot enough that gamma-ray photons spontaneously convert into electron-positron pairs. This pair production removes pressure support, causing catastrophic collapse and thermonuclear detonation that completely destroys the star without leaving a remnant. The explosion ejects processed material, including unusual element ratios, particularly odd-even effects in oxygen, magnesium, and silicon abundances that should appear in the spectra of stars formed from gas enriched by pair instability supernovae. The brief existence of population 3 stars left permanent imprints on cosmic evolution. Their deaths scattered the first heavy elements through pristine gas clouds, enabling subsequent generations to form stars more efficiently through metal line cooling. Their ultraviolet radiation began ionizing surrounding hydrogen, initiating the reionization process that would eventually make the universe transparent. Their black hole remnants, objects potentially 10 to 100 solar masses, formed from direct collapse of the most massive. Population 3 stars may have served as seeds for the supermassive black holes Webb observes in early galaxies. First starlight marks the universe's transformation from a dark, cooling expanse of neutral hydrogen into an environment where nuclear fusion created light, heat, and chemical complexity. The photons from these earliest stars traveled through expanding space for over 13 billion years, their wavelengths stretched by factors exceeding 14, arriving at Webb's mirrors as faint infrared whispers carrying information about the moment cosmic darkness gave way to the first sources of illumination in an otherwise lightless void. Cosmic dawn. 300 million years of darkness preceded cosmic dawn, the hidden beginning of light when the first stars ignited within primordial gas clouds and began reshaping the universe's chemical, thermal, and ionization state. The James Webb Space Telescope observes galaxies formed during and immediately after this transition, detecting objects at redshift Z exceeding 12, whose light originated when the universe was less than 400 million years old, capturing the epoch when gravitational collapse first produced temperatures and densities sufficient to initiate nuclear fusion. This wasn't simply the first appearance of stars. It represented a fundamental phase transition in cosmic evolution, from a universe governed purely by gravity and expansion to one where nuclear physics, stellar radiation, and chemical enrichment began determining how structure assembled and evolved. The timeline to cosmic dawn began immediately after the Big Bang. During the first 380,000 years, the universe remained too hot for neutral atoms to exist. Recombination created the first stable hydrogen and helium atoms, making space transparent to the cosmic microwave background. While leaving the universe dark, no stars yet existed to provide visible or ultraviolet light. Dark matter collapsed first, unaffected by radiation pressure, forming the gravitational potential wells into which normal matter would eventually fall. By 100 million years after the Big Bang, the first dark matter halos, massive enough to trap gas and initiate star formation, had assembled. These halos, called mini-halos, contained roughly 1 million solar masses concentrated within regions only a few hundred light-years across. Within these structures, molecular hydrogen formation proceeded through slow chemical pathways. Neutral hydrogen atoms occasionally formed molecular bonds, through three-body interactions or reactions on dust-grained surfaces, creating the only cooling mechanism capable of radiating gravitational heating in metal-free gas. Gas temperatures had to drop below several thousand Kelvin before gravitational collapse could overwhelm thermal pressure. The cooling timescale depended sensitively on molecular hydrogen abundance too little, and the gas remained too hot to collapse. Sufficient molecular hydrogen allowed gas to cool within the collapse timescale, enabling star formation. This threshold behavior meant cosmic dawn didn't occur simultaneously everywhere. It began in the densest regions where dark matter halos assembled earliest and molecular hydrogen formed most efficiently, then spread outward as more halos reached the critical mass necessary to trap gas and initiate cooling. The exact timing of cosmic dawn remains observationally uncertain. Webb detects galaxies at redshift z equals 13.2, corresponding to roughly 320 million years after the Big Bang, suggesting substantial star formation already occurred by this epoch. Theoretical models predict the very first stars might have formed as early as 100 million years after the Big Bang, though these earliest objects would be too faint for even Webb to detect individually. The galaxies Webb observes at extreme redshifts likely represent more massive systems that assembled after hundreds of millions of years of earlier, less vigorous star formation built up initial stellar populations. Cosmic dawn transformed the universe's physical state in multiple ways. Stellar ultraviolet radiation began ionizing surrounding hydrogen, creating the first ionized bubbles that would eventually merge during reionization. Supernova explosions from the deaths of massive first-generation stars injected kinetic energy into the intergalactic medium, heating gas and generating turbulence that affected subsequent star formation efficiency. Most importantly, stellar nucleosynthesis produced the first heavy elements, carbon, oxygen, iron, silicon, that would enable more efficient cooling, dust formation, and eventually the complex chemistry necessary for planets and life. The 21-centimeter line of neutral hydrogen offers a potential probe of the pre-dawn universe. Before stars formed, neutral hydrogen throughout space absorbed cosmic microwave background photons at this wavelength, creating absorption features in the background spectrum. When the first stars ignited, their ultraviolet radiation altered hydrogen's spin temperature, modifying the 21-centimeter absorption signal in ways that encode information about when and where star formation began. Ground-based radio telescopes search for these faint signals, attempting to detect the global 21-centimeter signature that would reveal cosmic dawn's timing and spatial structure. Cosmic dawn represents the universe's transition from simplicity to complexity, from a nearly uniform distribution of primordial hydrogen and helium to a structured cosmos featuring diverse stellar populations, chemical gradients, ionized and neutral regions, and the beginnings of galactic assembly. The photons Webb detects from this epoch traveled through 13 billion years of cosmic expansion, carrying information encoded when the universe first learned to make stars and the long darkness finally yielded to light. Deep field, looking into empty darkness for days on end, the James Webb Space Telescope performs deep field observations that see through 13 billion years of cosmic history by collecting photons that departed distant galaxies when the universe was barely a tenth of its current age. These aren't casual glances at the sky, they're extended exposures lasting dozens of hours focused on tiny patches of apparently empty space, allowing the telescope to detect objects hundreds of times fainter than anything visible in shorter observations. The technique exploits a fundamental principle. The longer you stare at darkness, the more light accumulates, and given sufficient time, even the faintest whisper of ancient starlight becomes detectable against the noise of random photon arrivals and instrumental background. The deep field tradition began with Hubble's original observations in 1995, when astronomers pointed the telescope at a seemingly vacant region in Ursa Major, measuring only 2.6 arc minutes across roughly 1/24th, the angular diameter of the full moon. Over 10 consecutive days, Hubble collected light during orbital passes totaling more than 100 hours of exposure time. The resulting image revealed not emptiness but approximately 3,000 galaxies, some so distant their light had travelled for over 12 billion years to reach Earth. The observation proved that apparently empty regions of sky actually contain thousands of faint galaxies invisible in shorter exposures. Webb extends this capability dramatically through infrared sensitivity and larger mirror size. The 6.5-meter primary mirror collects nearly 7 times more light than Hubble's 2.4-meter aperture, while infrared detectors capture wavelengths shifted by cosmic expansion beyond the range where Hubble's optical instruments maintain sensitivity. Galaxies at redshift Z exceeding 10 emit most of their light in ultraviolet and visible wavelengths, but by the time this radiation reaches Earth after crossing 13 billion light-years of expanding space, it has shifted into near-infrared wavelengths between 1 and 5 microns, precisely where Webb achieves maximum sensitivity. The Webb Deep Field, released in July 2022, captured a region of sky covered by a grain of sand held at arm's length. The exposure time totaled 12.5 hours, modest compared to Hubble's deep fields, but sufficient to reveal thousands of galaxies spanning cosmic history from the present day back to within 400 million years of K, the Big Bang. Some galaxies appear as large spirals or ellipticals relatively nearby in cosmic terms. Others manifest as faint red smudges marking extremely distant systems whose light departed during the universe's first billion years, their structures barely resolved even by Webb's angular resolution. Gravitational lensing amplifies the deep field's reach. The foreground galaxy cluster SMACS 0723, sitting roughly 4 billion light-years away, bends space sufficiently to magnify background galaxies aligned behind it from Earth's perspective. This natural cosmic telescope increases the effective brightness of distant galaxies by factors reaching 10 to 20, making objects detectable that would otherwise remain below Webb's sensitivity threshold even in extended exposures. The lensed galaxies appear as stretched arcs or multiple images surrounding the cluster, their distorted morphologies encoding information about both the lensing mass distribution and the source galaxy properties. Photometric redshift measurements extract distance information from galaxies too faint for spectroscopy. By measuring brightness through multiple filters spanning different wavelength ranges, astronomers identify the Lyman break, the sudden drop in flux, shortward of 91.2 nanometers in the galaxy's rest frame, where neutral hydrogen absorbs all ultraviolet photons. The observed wavelength of this break directly indicates redshift through the relationship between emitted and observed wavelengths set by cosmic expansion. Galaxies showing Lyman breaks at 1.3 microns sit at redshift Z approximately 10, corresponding to light that departed 550 million years after the Big Bang. The deepest fields push toward the earliest epochs accessible with current technology. Extended exposures totaling hundreds of hours might reveal galaxies at redshift Z approaching 20, corresponding to only 200 million years after the Big Bang, the edge of the Dark Ages when the very first stellar populations had just begun ionizing their surroundings. At these extreme distances, even Webb strains to detect individual galaxies. The photons arrive so infrequently and at such long wavelengths that distinguishing faint high redshift galaxies from foreground interlopers and instrumental noise requires sophisticated statistical analysis combining photometric measurements across dozens of filter combinations, searching for the distinctive spectral signatures that mark objects formed when the universe first learned to make stars. Infrared vision. Heat betrays presence. Every object warmer than absolute zero radiates electromagnetic energy at wavelengths determined by temperature, and infrared vision exploits this fundamental truth to reveal the universe as it actually exists, rather than as our evolved visual system perceives it. The James Webb Space Telescope operates entirely in infrared wavelengths between 0.6 and 28.5 microns, because this is where the hidden universe becomes visible, dust-obscured, stellar. Nurseries, cooling brown dwarfs, distant galaxies stretched by cosmic expansion, and the thermal glow from planets orbiting other stars all emit primarily in infrared bands that remain completely invisible to optical telescopes. Understanding why heat reveals truth requires understanding what infrared light actually is, and why the universe conspires to hide so much information in wavelengths our biology never evolved to detect. Blackbody radiation describes how temperature determines emission wavelength. Objects emit electromagnetic radiation across a broad spectrum, but the peak emission wavelength follows Wien's displacement law. Temperature times peak wavelength equals a constant, approximately 2.9 million nanometers Kelvin. Human bodies at 300 Kelvin radiate primarily around 10 microns in mid-infrared. The Sun's surface at 5800 Kelvin peaks in visible wavelengths around 500 nanometers. Interstellar dust at 50 Kelvin emits in far infrared around 60 microns. Webb's instruments span near and mid-infrared ranges, capturing thermal emission from objects between roughly 100 and 1000 Kelvin temperatures characteristic of forming stars, protoplanetary disks, and the surfaces of cool planets. Redshift shifts all wavelengths toward longer values through cosmic expansion. Galaxies at redshift Z emit light that arrives with wavelengths stretched by a factor of 1 plus Z. A galaxy at redshift Z equals 10 emits ultraviolet photons around 150 nanometers that arrive as near-infrared around 1.7 microns. Without infrared capabilities, these distant galaxies become invisible. Their emission shifted entirely beyond optical wavelength ranges. Hubble captured galaxies out to redshift Z approaching 12 through infrared instruments operating between 0.8 and 1.7 microns, but higher redshifts pushed emission into longer wavelengths, accessible only to Webb's extended infrared coverage. Dust extinction explains why infrared penetrates where visible light fails. Microscopic grains scattered through space absorb and scatter electromagnetic radiation most efficiently when grain sizes match photon wavelengths. Typical interstellar dust measures roughly 0.1 microns diameter, causing strong extinction in ultraviolet and visible wavelengths, while allowing infrared to pass relatively unimpeded. Dense molecular clouds showing optical extinctions exceeding 100 magnitudes, blocking 99.9999% of visible light, permit infrared transmission sufficient for Webb to observe. Protostars embedded within, revealing stellar birth happening in real time inside cocoons, completely opaque to every optical telescope ever built. Atmospheric absorption motivated space-based infrared astronomy. Earth's atmosphere contains water vapor and carbon dioxide that absorb mid-infrared wavelengths strongly, creating opacity bands where ground-based telescopes cannot observe, regardless of mirror size or detector sensitivity. The atmosphere essentially blocks wavelengths between 2.5 and 5 microns, and beyond 20 microns almost completely, except in narrow transmission windows. Space telescopes eliminate this limitation, accessing the full infrared spectrum and detecting features impossible to observe from the ground, particularly molecular absorption bands from water, carbon dioxide, and methane in exoplanet atmospheres. Cryogenic cooling maintains detector sensitivity. Infrared detectors measure photons by detecting the tiny temperature increases caused when photons deposit energy into detector material. Room temperature detectors emit their own thermal radiation that overwhelms faint astronomical signals. Webb's instruments operate at roughly 7 Kelvin, maintained by a massive sunshield blocking radiation from Sun, Earth, and Moon, simultaneously ensuring detector thermal emission remains far below the signals being measured. At these temperatures, materials behave strangely. Metals become superconducting, and gases freeze solid. But detectors achieve sensitivity capable of detecting individual photons, arriving after journeys lasting billions of years. The choice of infrared wavelengths wasn't arbitrary. It emerged from understanding what needed observing and where that information resided in the electromagnetic spectrum. The universe's most interesting phenomena emit primarily in wavelengths humans cannot see, hidden behind dust, distance, and cosmic expansion in regions of the spectrum, accessible only through technology that extends biological perception into realms evolution never prepared us to navigate directly. Behind Hubble, 30 years of discoveries left gaps wavelengths behind Hubble's capabilities, where entire populations of cosmic objects remained invisible despite the Space Telescope's revolutionary impact on astronomy. The James Webb Space Telescope fills these gaps not by replacing Hubble, but by extending observation into infrared wavelengths beyond 1.7 microns, the long wavelength limit where Hubble's instruments lose sensitivity and vast regions of the universe effectively disappear from view. Hubble transformed astronomy by observing from above Earth's turbulent atmosphere in ultraviolet, visible, and near-infrared wavelengths, revealing galaxies, nebulae, and stellar populations with unprecedented clarity. Yet its optical and near-infrared design meant dust-shrouded star formation, the most distant galaxies, cool stellar remnants, and planetary atmospheres emitting primarily in mid-infrared wavelengths remained largely inaccessible throughout its 3-decade mission. The wavelength gap between 1.7 and 28 microns contains critical information about cosmic evolution. Galaxies at redshift Z exceeding 7 emit most of their light in wavelengths beyond Hubble's range. Their ultraviolet and visible emissions stretch by cosmic expansion into mid-infrared bands. Hubble detected hints of these objects through photometric techniques, pushing its infrared instruments to their limits, identifying candidate high redshift galaxies, requiring spectroscopic confirmation that only longer wavelength observations could provide. Webb's instruments operate precisely in this wavelength regime, capturing light from galaxies formed during the universe's first billion years that Hubble could barely glimpse. Dust extinction hides star formation from optical telescopes regardless of sensitivity or angular resolution. Molecular clouds where stars currently form contain dust concentrations, blocking visible light completely while remaining transparent at mid-infrared wavelengths. Hubble observed stellar nurseries like the Eagle Nebula's pillars of creation in exquisite detail, revealing illuminated surfaces and the outer structure of these cosmic monuments. Webb penetrates the pillars themselves, exposing dozens of embedded protostars invisible to Hubble, stars in the process of formation still buried within their natal material, their existence revealed only through infrared emission that optical instruments cannot detect. Temperature determines emission wavelength through blackbody radiation physics. Objects at room temperature radiate primarily around 10 microns squarely in mid-infrared. Brown dwarfs, failed stars too small to sustain hydrogen fusion, cool over billions of years until their surface temperatures drop below 1000 Kelvin, shifting peak emission beyond Hubble's sensitivity range. Hubble discovered the nearest and brightest brown dwarfs through near-infrared observations, but cooler, more distant objects remained undetectable. Webb's extended wavelength coverage reveals populations of ancient cool brown dwarfs pervading the galaxy, objects that formed billions of years ago and have been cooling toward invisibility ever since. Exoplanet atmospheres emit and absorb primarily in infrared wavelengths where molecular transitions create characteristic spectroscopic signatures. Water vapor shows strong absorption features at 1.4, 1.9, and 2.7 microns. Carbon dioxide absorbs at 4.3 microns. Methane creates distinctive patterns across multiple mid-infrared bands. Hubble detected water vapor in a few giant exoplanet atmospheres through near-infrared observations, but the strongest molecular features lie in mid-infrared wavelengths beyond its range. Webb accesses these diagnostic wavelengths directly, characterizing atmospheric compositions with detail impossible through optical or near-infrared spectroscopy alone. The angular resolution advantage Hubble maintains at visible wavelengths becomes less significant at longer wavelengths, where diffraction limits set minimum resolvable angles. Webb's larger mirror diameter compensates for this wavelength effect at 2 microns. Webb achieves angular resolution comparable to Hubble at visible wavelengths, while extending to 28 microns, where Hubble cannot observe at all. The two telescopes complement rather than compete, Hubble providing superior resolution in ultraviolet and visible bands, Webb dominating infrared wavelengths where the universe's hidden structures finally become visible. Hubble's legacy includes 30,000 published papers and discoveries that reshaped cosmology, yet even its extraordinary capabilities left questions unanswered because the relevant wavelengths lay beyond its design parameters. Webb doesn't diminish Hubble's achievements, it fulfills them, observing the wavelengths where answers to Hubble's questions have been waiting throughout the Space Telescope's remarkable career, hidden behind the 1.7 micron boundary where optical astronomy ends and the infrared universe begins. Universe unmasked. Every hidden layer revealed by the James Webb Space Telescope, dusty stellar nurseries, ancient galaxies, cool planetary atmospheres. The cosmic web's dark scaffolding assembles into a complete picture that unmasks the universe as it actually exists, rather than how our limited perception construes it. The cosmos isn't composed primarily of luminous stars and glowing nebulae visible to optical telescopes. It's dominated by structures invisible at visible wavelengths, dark matter outweighing normal matter by factors of 5, molecular clouds shrouded by their own dust, galaxies whose most vigorous star formation occurs behind opaque veils, and the chemical complexity of planetary atmospheres readable only through infrared spectroscopy. Webb's observations don't simply add details to an existing picture, they fundamentally revise what the picture contains. revealing that most cosmic activity occurs in wavelengths biological vision never evolved to perceive. The hidden reality begins with recognizing that visible light represents an arbitrary slice of the electromagnetic spectrum, meaningful to humans because our star happens to emit peak radiation in these wavelengths, and Earth's atmosphere transmits them efficiently. Physics doesn't privilege visible wavelengths, they carry no more intrinsic information than ultraviolet, infrared, or radio emissions. The universe generates electromagnetic radiation across dozens of orders of magnitude in wavelength, from gamma rays measuring picometers to radio waves spanning kilometers. Each wavelength regime reveals different physical processes. Gamma rays trace nuclear reactions and particle acceleration. X-rays mark hot plasmas and black hole accretion. Visible light captures stellar photospheres. Infrared reveals thermal emission and dust-penetrating views. Radio wavelengths probe cold molecular gas and magnetic fields. Webb's infrared observations expose structures that optical astronomy misses entirely. Ghost galaxies systems so dust-obscured they appear as voids in visible light surveys, despite containing billions of stars undergoing intense star formation, emerge in infrared images as brilliant sources, their stellar populations finally visible through the dust that blocks optical photons. These aren't rare curiosities. They represent perhaps 20 to 30% of galaxies during peak cosmic star formation epochs, populations that contribute substantially to the universe's total stellar mass budget, yet remained essentially invisible until infrared instruments finally captured their thermal emission. The universe's thermal state becomes readable through infrared wavelengths. Every object radiates according to its temperature, creating a cosmic landscape of thermal signatures ranging from the 3 Kelvin cosmic microwave background through 100 Kelvin protoplanetary disks to 1000 Kelvin stellar atmospheres and million Kelvin accretion disk coronae. Optical astronomy captures only the hottest visible surfaces, stellar photospheres and ionized gas clouds. Infrared observations reveal cooler structures, forming stars still embedded in collapsing clouds, planetary atmospheres ranging from freezing ice giants to scorching hot Jupiters, brown dwarfs cooling toward temperatures barely warmer than room conditions, and the dust grains that absorb stellar radiation and re-radiate energy as infrared thermal emission. Chemical complexity requires infrared spectroscopy. Molecules absorb and emit primarily at infrared wavelengths where vibrational and rotational transitions occur. Water, carbon dioxide, methane, ammonia, complex organics, all the molecular species that determine atmospheric composition, enable organic chemistry, and potentially support biology leave their strongest spectroscopic signatures in infrared bands. Visible light spectroscopy captures electronic transitions in atoms and simple ions, but misses the molecular information encoded in infrared absorption features. Understanding what comprises planetary atmospheres, what molecules exist in stellar outflows, which organic compounds pervade interstellar space, all require infrared observations that reveal the universe's chemical inventory. Cosmic history becomes accessible through redshift. Light from distant galaxies arrives stretched by cosmic expansion, wavelengths multiplied by factors exceeding 10 for the most distant objects. Ultraviolet photons emitted by hot young stars in galaxies formed during the universe's first billion years arrive as near-infrared radiation after crossing 13 billion light-years of expanding space. Without infrared capabilities, the early universe remains observationally inaccessible. Its emission shifted entirely beyond optical wavelength ranges. Webb's infrared instruments capture light from epochs no optical telescope can observe, revealing galaxy formation and evolution during the universe's infancy, when structures first assembled from primordial gas. The complete picture integrates observations across all wavelengths, each contributing unique information about different physical processes, temperature regimes, and cosmic epochs. Optical astronomy provided humanity's first comprehensive view of the universe beyond Earth, revealing stars, galaxies, and nebulae in glorious detail. Yet it showed only one facet of cosmic reality, the narrow band where hot stars radiate and human eyes respond. Webb unmasks the broader reality. The universe as it exists across the full electromagnetic spectrum, dominated not by visible light but by infrared thermal emission carrying information about dust, molecules, cool objects, and ancient starlight that optical astronomy alone could never reveal.